Let's start the third video of Chapter 4, Section 1. Now that we've defined absolute extreme values and local extreme values, let's figure out how to find them. So in this section, we're going to see definitions of critical point and stationary point. We're also going to look at a theorem called local extreme values. We're also going to look at a test called the candidate's test for absolute extrema that will help us find absolute extrema on a given interval. So first we want to begin here. The interior points where the function on the image from slide 13 has local extreme values are points where either f prime is 0 or f prime does not exist. And let's go back to that slide and that image to see if that's true. So slide 13 is here. This is the graphic. Where there are local extremas, such at x value c, we can probably believe that f prime is equal to 0 because the tangent line here is horizontal. So I'm going to make a note, f prime is 0. Here's a local minimum value at x equals e, and we can probably again believe that f prime is 0 here because the tangent line is horizontal. F prime is 0. And then another absolute maximum, or actually relative maximum, 2, here at x equals d, has a point where we could believe that f prime does not exist because we can see that a tangent line coming in from the left or derivative from the left would not match up with derivative from the right. So we would have f prime does not exist. And so that sentence then at the beginning here of 413 makes sense. And it turns out that this is generally the case, as we see in this following theorem, which was discovered first by Fermat. If a function f has a local maximum value or local minimum value at an interior point C on its domain, and f prime exists at C, then f prime of C is 0. So because of this theorem, we usually need to look at only a few points to find a function's extrema. That's kind of great because we don't want to check every single point on an interval. These points that we're going to check consist of the interior domain points where either f prime is equal to 0 or f prime does not exist. Those are the 2 points by the previous theorem. And then also the endpoints of the domain. So sum it up. It's f prime 0. It's f prime does not exist. And its endpoints. Those are the only places where those maximums and minimums could possibly occur. At all other domain points, f prime is going to be either positive or negative. So that leads us into wanting to clarify some of our findings a little bit better. We're going to introduce some vocabulary terms. First, and the biggest one, is critical point. A point that's in the interior of a domain of a function where f prime is either 0 or f prime doesn't exist, we are now going to refer to as a critical point. So it's if f prime doesn't exist or if f prime is 0 at a particular value, then we have a point that we're going to call a critical point. So in summary, extreme values only occur at critical points and endpoints. That's a quicker and easier way to say what we ended the last slide with. Also a stationary point. So a stationary point is a point in the interior of the domain at which the function's derivative f prime is 0. So that kind of discludes the f prime does not exist. So if f prime is just 0, that's going to be a stationary point. But I will warn you that for the most part, we use critical point a lot more than we use the term stationary point. We want to say here that a stationary point could be a minimum, it could be a maximum, or it might actually be neither. And we're going to see some examples of functions where we get neither of those. So we also want to note that critical points and stationary points are not necessarily the same, and we're going to see that as well. So finding those extreme values, taking into consideration what we have from the previous few slides. We've got a theorem, we've got some new vocabulary. The extreme value theorem is going to guarantee that a continuous function on a closed interval must have both a maximum value and a minimum value. And the theorem on the previous slide, slide 16, I guess it was 2 before, guarantees that those values can only occur at critical points and endpoints. So that feels to me like two things that ought to be put together. The extreme value theorem guarantees that we have a maximum and a minimum. And then the theorem from slide 16 says that those points, the maximum and minimum, can only occur at critical points and endpoints. Therefore, to find those absolute extrema of a function on a closed interval, it suffices to just compare the function values at these, what we're going to call candidate points. They are the candidates for where we might see the absolute extrema. And therefore, we have something called the candidate's test. The absolute extreme of a function f on a closed interval can be determined by evaluating the function at each critical number. So we want to evaluate the function at each critical number and at each endpoint of the interval. The maximum of those values is the absolute maximum, and the minimum of those values is the absolute minimum. This is the candidate's test. So here's an example, and we're going to apply the candidate's test for the first time. Find the absolute maximum and minimum values of f of x is equal to x to the power of 2/3 on the closed interval -2 to 3. So we know that we're going to test -2. We know that we're going to test +3. Those are the endpoints of our interval. But we also want to test any critical numbers that might occur inside that interval. So what we want to do is first find the derivative of this function and see if it might be 0 or not defined at any of the points inside -2 to 3. So the derivative by power rule is 2/3 x to the power of -1/3, which can then be simplified to 2/3x to the power of 1/3. So if this derivative were equal to 0, then the numerator would be 0. Well, 2 = 0 doesn't make sense, so f prime is not 0, apparently. If this derivative was not defined, then we have 3x to the 1/3 equal to 0, because we would have 2 divided by 0. That would be undefined. And this actually does happen. It occurs where x is equal to 0. Is x equals 0 inside of our interval? Yes, it is. So now we have 3 candidates that we're going to test for absolute minimums and absolute maximums. And usually we organize a candidate's test in a table. We have x values and we have y values, or other words, f of x values. And our x values that are the candidates are the left endpoint, which is -2. The critical number inside, which is 0, and then the right endpoint, which is 3. In the right column, we want to find the function values, not the derivative, but the actual function. So what is f of -2? So we plug -2 into the function. We get -2 to the power of 2/3, which we could actually write as the cube root of 4, since -2 squared is 4, and then to the 1/3 power is a cube root. Next, f of 0. We have 0 to the 2/3, and that's, of course, 0. And then we want f of 3. So 3 to the 2/3 power is going to be the cube root of 9, because 3 squared is 9. Now, here's what we do to end the candidate's test. Look at these 3 values. The candidate's test said that the maximum of these values is the absolute maximum. And so if I compare these, 0 is the smallest, then the cube root of 4, and then the cube root of 9. So what we want to say here for an answer is the absolute maximum, absolute max, is the cube root of 9, and it occurs, or we'll just say at x equals 3, and then we'll say the absolute minimum, the absolute min, is, now let's go to the other two, is smaller value 0 or cube root of 4. It's 0. The absolute min is 0, and that's at x equals 0. Very nice, and we have an answer to that one. Now let's try exercise 11 from the text. We want to use the candidate's test to find extreme values of this function on the given interval and where they might occur, and then identify any critical points that are not stationary points. So here we go. First things first, we want to do a derivative. So f prime of x is equal to this 1 over x. I'm going to think of as x to the power of -1. So its derivative by the power rule is negative x to the -2nd. And then plus the derivative of natural log of x is, of course, 1 over x. And now we want to find out if this is either equal to 0 or if it's undefined, anywhere between 1/2 and 4. So I'm going to rewrite this a little bit so that I can do some algebra here. So I think I can rewrite this as -1 over x squared plus 1 over x. And then a common denominator between these two fractions would be x squared. So that means we want to multiply by x here and by x there. We have -1 plus x in the numerator, and we have x squared in the denominator. So is there anywhere that this derivative might be equal to 0? And I say yes, it's 0 when x is equal to 1, because -1 plus 1 would be 0. Is the denominator 0 anywhere? That would be the answer to the question, is it undefined? And yes, it is. It's undefined at x equals 0. So are either of these points inside the domain that we are looking at the function from 0.5 to 4? X equals 0 is definitely not. As a matter of fact, it's not in the domain of the function itself because, well, we can't take the natural log of 0, and we also can't do 1 divided by 0, so it's kind of out already. But x equals 1 is a candidate. So let's set up the candidate's test. We have an x f of x table, and we're going to look at a left endpoint of 0.5 or 1/2. And then we're going to look at a critical number of 1. And then we're going to look at a right endpoint of 4. So what are these function values? F of 0.5 or f of 1/2 would be 1 over 0.5 or 1 over 1/2 plus the natural log of 0.5. And let's see then, f of 1 would be 1 over 1 plus the natural log of 1. And then f of 4 would be 1 over 4 plus the natural log of 4. And I'm going to use my calculator to help me out with these values. So we want first 1 divided by 0.5 plus the natural log of 0.5, 1 divided by 0.5 plus the natural log of 0.5. And this is going to be about 1.306. 1.306. Next, we want 1 over 1 plus the natural log of 1. So let's go back here. 1 over 1 plus the natural log of 1. I think I know this one already. And yeah, it's just 1 because the natural log of 1 is 0. So that's 1, and we'll change this to equals. And then we want 1/4 plus the natural log of 4. 1 divided by 4 plus the natural log of 4. And that's 1.636 on that one. So 1.636. So where are we at in this candidate's test? Looks to me like I have a maximum value there, and the minimum value here is 1. So we want to give an answer of that. We have an absolute max of 1.636 at x equals 4, and we might even say approximately. And then we have an absolute minimum of 1 at x equals 1. And we want to be sure when we take questions such as this that we're really answering what is asked for. Sometimes it's what's the value, sometimes it's where does it occur, and maybe even in multiple choice questions we might see this maybe like the second answer is given as f of 1 equals 1. We just want to make sure that you are reading closely and saying, do we want where the absolute maximum is? Do we want what the absolute maximum is? Pay careful attention to that. Here's another one, example 4. Find the extreme values of f of x is equal to 1 over the square root of 4 minus x squared. And then down here below, graph this function in Desmos and then a TI-84 to see graph or failure. So we are going to graph this in our calculator, but first let's start with the candidates test, and we want to find derivatives. So I'm going to rewrite this function as 4 minus x squared to the negative 1/2 power first. That's a square root on the bottom, so that changes to an exponent of a half. Bump the whole thing to the numerator. That allows me to use the chain rule instead of the quotient rule with a chain rule. So f prime of x in this case is going to be equal to negative 1/2 times a 4 minus x squared. Now that's to the power of negative 3/2. And then by the chain rule times a negative 2x. So that's going to simplify into, well, negative times negative is positive. 1/2 times 2 is 1. So that's an x in the numerator. And then that's a 4 minus x squared to the positive 3/2 in the denominator. So is this ever 0, the derivative? Yes, it is. That's at x equals 0. Is it ever undefined? So is the denominator 0? Yes, it is when x is plus or minus 2. So are either of these values, or I guess any, since it's negative 2, 0, and 2, candidates for an extreme value? And it turns out that only 0 is, because take a look at 2 and negative 2. Well, 2 and negative 2 going into f give us 4 minus 4 in the denominator. So that's 0 in the denominator. These are not part of the domain. And I believe we could get ourselves around to the idea that this function only ever exists on the open interval from negative 2 to 2. Anything between those two values work, but once we get to the right of 2 or to the left of negative 2, we're taking the square root of a negative value. Again, I'm going to confirm that in my TI-84. So we're going to go to y equals, let's clear that out. I want to graph 1 divided by the square root of 4 minus x squared. And let's take a look at this on Zoom Decimal. That's option 4. So there it is. And a little strangeness here. I think it looks like this graph kind of stops. It doesn't actually. I'll do a little quick sketch over here that this function actually, let's see, negative 1, negative 2, 1, 2. This function actually looks a little bit like this, and there are asymptotes here. It doesn't stop like what we see on this graph, but that's kind of what we mean by grapher failure, that the TI calculators are only able to do so much given their pixel inefficiencies, and they can only have so many points on that screen. So there's really only one point here that I see as a possible extreme value. I think there's a minimum right there. There is no left endpoint or right endpoint to check, which I guess is a good thing. So what is f of 0? Well, let's see. That's 1 over the square root of 4 minus 0 squared. So we got 1 over the square root of 4 minus 0 squared. So that's going to be 1 over the square root of 4, which is a half. So that means we have a minimum. It's both a relative minimum because it's smaller than all the values around it, and it's also an absolute minimum. That's what I'm going to give as an answer, an absolute min of 1/2 at x equals 0. And that's how I'm going to finish up that example 4. I'm going to leave exercise 25 to you. And as a matter of fact, I'm going to leave 413 extreme values and critical values along with the examples that go after to you to take a look at on page 206 and 207 of your text or in class, and that will do it for this video.